In the previous video, we explored the relationship between the shape of the gradient function and the original function. So in this, we're just going to explore that in a little more detail with some more examples. So most of this material that I've got on the screen here has come from Mathematical Methods Dimensions Units 3 and 4 by Pearson Longman in 2006. So any cut and paste are from that resource, and other materials are my own. Now, we saw that if we have the function y equal to x, its derivative is the y dx equal to 1, and because y equal to x is a straight line, then its gradient function, then there's the graph of y equal to x, and its gradient function then is simply a horizontal straight line because it's an equation equal to 1. Similarly, we saw that when we looked at the graph of x squared, here we see it here, we can see for values of x less than 0, it has a negative gradient, and values of x greater than 0, it has a positive gradient. And because its derivative is 2x, the shape of that graph is a straight line, and we can see down here, this part here represents the gradient around here. So obviously a point up here would be a more negative number, and as we get towards the origin, the values are getting smaller, and then once we get past the origin, it starts to become positive again, and as x gets larger, the graph is getting steeper. So here it is here, and there is the gradient function. So if we take this particular point here, its gradient graph is saying that at x equal to -3, reading off on the graph, its gradient then is -6. If I move that line in a little closer, so imagine there's a tangent at the point -2. So at -2, we expect that the slope of that line, -2, would mean that moving a line up to here, it reads off that the gradient is -4. And if I keep moving that line in, move it into, let's go over here, say to x equal to 1. We expect now that at x equal to 1, moving our line up, here we go, at x equal to 1, there it is there. The gradient at this particular point, then it should be, here it is, it's got the value of 2. Now the cubic, if you remember, its derivative is 3x squared. Here is the gradient, sorry, here is the graph of the cubic. So if we take it, say, at x equal to -2, we can see that this part of the graph around here is going to have a positive gradient. So at x equal to -2, if I come down and read off what its value is on the derivative graph, it would slightly up here, so it actually would be about 12. So if I come in, say, to x equal to -1, look, putting in the equation, we expect that -1 squared is 1/3. We expect the gradient to be 3, and if we read off 1, 2, 3, that's what the gradient function to y dx is telling us the slope at that point. Then at x equal to 0, it's 0, and then as we go around here, this graph has a positive gradient again. So this is what we call a stationary point of inflection, because the gradient sign hasn't changed. It's been positive, 0, then it's positive again. So at -1, if I move it up, and we see that it's got the value of 3, which is what we expect when we substitute in x equal to 1. So we can see then that when x is negative, the derivative was positive, the slope was positive. At x equal to 0, the derivative was 0. And for positive values of x again, the derivative is positive again. Now let's explore this cubic here. We've got x negative 3 times x minus 1 times x plus 2, which when expanded is equal to x cubed minus 2x squared minus 5x plus 6. Here you can see the thing is drawn. Intercepts are at negative 2, at 1, and at 3. And A represents the turning points where the origin 0, so that's roughly negative 0.8 for that one. And this one over here is sort of roughly 2. So when we expand those brackets, it's the equation. So when I take the derivative, I get 3x squared minus 4x minus 5. And of course, the shape of that graph is parabolic. And here it is down here. Now, around here at x equal to a, we know that it's a turning point, it's a stationary point, it's a local maximum there. So this part around here, the graph has a positive gradient. So at negative 2, this doesn't quite fit on the graph there, so let's come into that point. So reading off there tells me what its gradient is at that particular point, which is what I expect to be a positive value. At x equal to a, we can see that the gradient is 0. Now, between a and b, the graph around here has a negative slope, and this is what we see with the graph here. The derivative graph is below the x-axis, which is showing that between a and b, the gradient function has negative values. So if I took that particular point there, reading off down here, it's got a gradient at that point of roughly negative 7. At 1, it's roughly the same again. We can see that at B, a dotted line crosses the x-axis, so the gradient is negative again. And then for B greater than 0, this part of the graph, a tangent then would have a positive gradient, and we can see that the gradient function is positive again. So for x less than a, here it is here. So each of these 2 points here correspond to a and b. So for x less than a, the gradient is positive. Then between a and b, it's negative, reflected by the part of the parabola under the graph. And then for greater than b, then it becomes a positive gradient again. Okay, let's look at this example here which says sketch the gradient function for the quadratic shown below. Now we can see that it's an inverted quadratic and it's got a turning point or a vertex at x equal to 1. So that suggests that its equation is similar to something like negative, because it's upside down, x minus 1, because it has a turning point at 1, and then we don't know what the y value is, so I'm just sort of guessing there that's true, but it's going to be of that form. So when we take the derivative of that, we get that it would be negative 2x minus 2. So what it's saying is, if we put that equal to 0, that would tell us that the gradient is 0 at 1, which is what this is showing here. And we can see that this part of the graph around here has a positive gradient. So for x less than 1, the gradient is going to be positive. And for x greater than 1, the gradient is going to be negative. So you can see that if you graph negative 2x minus 2, it's a straight line. It's going to go in that direction. So that when we graph it, here it is here. So we know that the derivative is 0 at 1, which reflects that. We know around here that the gradient, the slope of that graph for x less than 1 is positive. So when we look at gradient graph here for x less than 1, our blue line is above the x-axis, which means that it's telling us that the gradient is positive. And over here we can see that when x is greater than 1, our graph around here is going to have a negative value, which is what our gradient graph is showing here. So for x less than 1, it's telling us that the gradient of the graph is negative. So to work something out like this, you need to understand that if it's a quadratic, when we take its derivative, it's going to be a linear equation. So by analysing when it's positive, when it's negative, we can work out if a graph goes this way or that way. Now in this example, it suggests a cubic, and it's suggesting that it has a turning point at -2, another turning point at 1, and we know that for a cubic, when we take its derivative, you would get something like, well, the derivative of x cubed is 3x squared, so we know that the gradient function of this is going to be of the form of a quadratic. Now, we can see that when a derivative is negative between -2 and 1, so we can see between -2 and 1, our graph here has a negative gradient. So that means that the gradient function between -2 and 1 has to be below the x-axis to reflect a negative value. And we can see that it's got a positive gradient there when x is less than -2 and when x is greater than 1. So that, therefore, when we sketched the thing, we knew that it was going to be parabolic in shape. -2 and 1 are the two turning points here, and it's got a negative gradient, hence the graph is below the x-axis between -2 and 1, positive for greater than 1, and positive again when x is less than negative. So what you can now do is have a go at exercise 19C, question 527. And on Study Smart, you'll also find another worksheet. I'll do a quick video of that, of some more graphs where you can practice determining what the shape of the gradient function looks like for each of those graphs.